Hi everyone, I'm Gili and I'm going to talk about generic group identity-based encryption, a tight impossibility result. This is joint work with Gili Segev. Let's start by quickly reviewing the notion of identity-based encryption. The notion of identity-based encryption proposed by Shamir back in 1984 extends the classic notion of public key encryption by essentially allowing any string to be used as a public key. An IBE scheme consists of 4 algorithms. The first algorithm is a setup algorithm that generates the public parameters which are given as input to all other algorithms and a master secret key which is kept private. The second algorithm is a key generation algorithm that takes as input an identity ID and the master secret key and generates a corresponding identity secret key SKID. The third algorithm is the encryption algorithm that takes as input an identity ID and a message M and produces a ciphertext. Finally, the fourth algorithm is the decryption algorithm that takes as input an identity secret key and a ciphertext and outputs a message. The main challenge when designing IBE schemes is to keep the public parameters as short as possible. In particular, the public parameters should not scale linearly with the number of users, and intuitively, this is the key property that distinguishes identity-based encryption from public key encryption. Ideally, the public parameters should, in some sense, compress exponentially many public keys, thus allowing any bounded length string to be used as a public identifier for the purpose of asymmetric encryption. For nearly 2 decades, Shamir's version of designing identity-based encryption schemes seemed completely out of reach. This dramatically changed with the breakthroughs of Boneh and Franklin and Cox, who constructed the first IBE schemes. Boneh and Franklin constructed an IBE scheme based on the hardness of the bilinear Diffie-Hellman problem in prime-order bilinear groups, and Cox constructed an IBE scheme based on the hardness of the quadratic residuosity problem in RSA groups. Following their pioneering work, extensive research has been devoted to constructing IBE schemes based on a wide range of computational assumptions and to extending the notion of identity-based encryption to support more expressive functionalities. Throughout this impressive journey, a long-standing open problem was whether or not an IBE scheme can be constructed in prime-order groups without relying on bilinear maps. Prime-order groups without bilinear maps are extremely well studied in cryptography and admit a variety of instantiations and constructions with them, dating all the way back to the Diffie-Hellman key exchange protocol and ElGamal encryption. Luckily, this foundational challenge was resolved by ttling and Garg 4 years ago. In their breakthrough result, they constructed an IBE scheme and even a hierarchical one based on the hardness of the Diffie-Hellman problem in prime-order groups. Despite this surprising progress, a substantial gap still remains between the cryptographic techniques that are known to imply public key encryption in prime-order groups and those that are known to imply identity-based encryption in such groups. Specifically, whereas ElGamal encryption and the Boneh-Franklin IBE scheme treat their underlying groups in an intuitive black box manner, the ttling-Garg IBE scheme exploits the concrete representation of group elements. This distinction is captured by Shup's notion of generic group algorithms, capturing all algorithms that do not rely on any specific property of the representation of the underlying group. It should be noted that, from a practical perspective, generic group constructions are typically more practically relevant when compared to non-generic ones. This is especially noticeable for the ttling-Garg IBE that relies on non-generic garbling techniques. Additionally, from a more foundational perspective, Generic group constructions tend to be somewhat simpler and more direct when compared to non-generic ones, thus potentially leading to additional insights on the problem at hand. At this point, an interesting question that arises is whether or not an IBE scheme can be generically constructed based on the hardness of the Diffie-Hellman problem. Note that, in fact, any public key encryption scheme can be used to construct a somewhat trivial identity-based encryption scheme, where the length of its public parameters scales linearly with the number of identities. In particular, ElGamal encryption yields a generic group IBE scheme that supports NPP identities and whose public parameters consist of NPP group elements, not including the group's generator. Therefore, we need to refine our question by considering non-trivial generic group IBE schemes. Schemes that support more than NPP identities with public parameters that consist of NPP group elements. Initial evidence for the difficulty of constructing IBE schemes without bilinear maps or other specific forms of structure was provided by Boneh et al. They showed that an identity-based encryption scheme cannot be constructed in a black box manner based on trapdoor permutations or CCA secure public key encryption. Then, from a more algebraic perspective, Papakonstantinou et al. Studied the problem in which we are interested in this work, the feasibility of constructing generic group IBE schemes. They showed that there are no generic group IBE schemes supporting an identity space of exponential size. In fact, their result seems to hold already for identity spaces of sufficiently large polynomial size. However, their work left completely unsolved the question of whether or not any non-trivial generic group IBE scheme can be constructed. In this work, we resolve this question by proving a tight impossibility result for constructing generic group IBE schemes. We show that any such scheme, whose public parameters consist of NPP group elements, may support at most NPP identities. This matches the trivial threshold that is obtained, for example, by including an independent ElGamal and public key for each identity. Compared to the work of Papakonstantinou et al., on the one hand, our proof follows the structure of their proof, which I will discuss in a few slides. On the other hand, however, our result does not only provide a tight threshold, but in fact provides a somewhat more direct technical description of our attack and of its analysis. Such a description is enabled partially due to the fact that we prove our result within Maurer's generic group model, whereas Papakonstantinou et al. Proved their result within Schup's incomparable generic group model. Roughly speaking, as we will see in a few slides, in Maurer's model we do not have to take into account the additional randomness that is somewhat artificially injected into cryptographic computations in Schup's model due to its random injective encoding of group elements. The rest of this talk will follow this outline. We will start by defining the generic group model within which we prove our result. Next, we will define in more detail identity-based encryption schemes within this model. Then we will present a simplified high-level overview of our proof. So let's begin by discussing the generic group model. A generic group algorithm is an algorithm that does not exploit the representation of the underlying group in any way. This is captured via an oracle which manages the access of all algorithms to the group. In this work, we use the generic group model suggested by Maurer. In this model, group elements do not have an explicit representation, and instead, algorithms specify their queries by pointing to previously seen group elements. For example, an algorithm may ask the oracle to apply the group operation to the 4th element and 7th element that have appeared in the computation so far. This model is a bit different from the generic group model originally suggested by Shoup. In Shoup's model, each group element has an explicit random representation. These two models have been shown to be polynomially equivalent for certain problems, such as the discrete logarithm problem, but in general, the two models are incomparable. When proving lower bounds for cryptographic primitives, which is our goal in this work, Mauer's model enables us to focus on the algebraic structure of the primitives while eliminating the potentially significantly yet somewhat unintentional implications of the artificially added randomness in Shoup's model. In other words, Mauer's model ensures us that the security of primitives within it is based on their algebraic structure and not potentially on the fact that group elements have completely random representations, which is clearly not the case in any concrete group. Let's define the model a bit more formally. Any cyclic group of order n is isomorphic to the additive group Zn, and therefore group elements in this model are identified with the elements of the additive group Zn. A generic computation is associated with a table B of Zn elements managed by the oracle. This table B is initialized with the Zn elements corresponding to the input elements that are provided to an algorithm, and the table is always initialized with the generator 1 at its first entry. A generic algorithm can then issue two types of queries to the oracle: group operation queries and equality queries. To issue a query, an algorithm specifies the indices in the table of the two elements that it wishes to compare, or to which it wants to apply the group operation, and the type of operation plus or minus. In response to a group operation query, the oracle adds or subtracts the two corresponding elements in the table and places the result in the next vacant entry. In response to an equality query, the oracle compares the two Zn elements from the table and answers accordingly. When a generic algorithm wants to output a group element, it outputs the index of the corresponding entry in the table B. In addition to group elements, algorithms may receive as input or include in their output also explicit bit strings. This model also naturally captures interactive computations, allowing one generic algorithm to pass group elements to another generic algorithm by pointing to elements in the table B. In this work, we consider the case of known order groups of prime order, in which the order n is a prime number that is provided as an explicit input to all algorithms. Having introduced the basic ideas underlying the generic group model, we can now recall the notion of identity-based encryption within it. A generic group IBE scheme consists of four generic group algorithms: setup, keygen, encrypt, and decrypt. The setup algorithm receives as input the security parameter lambda and the order n of the group, and outputs public parameters and a master secret key. The key generation algorithm receives as input the public parameters, the master secret key, and an identity, and outputs an identity secret key, SKID. The encryption algorithm receives as input the public parameters, an identity, and a message, and outputs a ciphertext. Finally, the decryption algorithm receives as input the public parameters, an identity secret key, and a ciphertext C, and outputs a message M. In terms of correctness, we consider the standard notion of correctness that allows a decryption error. In terms of security, as standard in the generic group model, we consider generic group adversaries that may issue a polynomial number of queries and are unbounded in terms of their additional internal computation. We ask that any such adversary wins the following experiment with only a negligible advantage. First, the adversary specifies a challenge ID star and a polynomial number k of additional identities, ID1 to IDK, for which the adversary will obtain corresponding identity secret keys. Then, the setup algorithm generates a master secret key and public parameters, which are then used to generate identity secret keys for the K identities ID1 to IDK. The adversary receives the public parameters and the K identity secret keys together with an encryption of a randomly chosen bit B for the challenge identity. At this point, the adversary outputs a bit B prime, and we say that the adversary wins if B primes equal B. Notice that we consider a rather weak notion of security in which adversaries are non-adaptive in their choice of both the challenge identity and the identities for which secret keys are provided. Since we prove an impossibility result, this only strengthens the result. Okay, so we can now move on to a simplified high-level overview of the main ideas underlying our proof. Let me just note once again that for the purpose of this talk, we present a simplified variant of our proof, and please see the full version of our paper for a more complete overview and for a formal proof. We follow a two-step structure similar to that introduced in the work of Papakonstantinou et al. First, in step 1, we show that any generic group IBE scheme can be transformed into one in which secret keys do not contain group elements. Our transformation modifies the secret keys and modifies the decryption algorithm, but does not modify the public parameters or the encryption algorithm. Thus, given step 1, we are left to prove our result for schemes in which secret keys consist only of explicit strings. Then, in step 2, we present an attack on any such scheme that supports more identities than the number of group elements included in its public parameters. The remainder of this talk consists of a high-level description of these two steps, and let's begin with step 1, in which we prove the following lemma. Any generic group IBE scheme that has decryption error epsilon and whose public parameters consist of NPP group elements can be transformed into a generic group IBE scheme over the same identity space with the decryption error epsilon plus 1 over p for any predetermined polynomial p with the same number NPP of group elements in its public parameters and without any group elements in its secret keys. The main idea of the construction, as we will see in the following slides, is to replace each secret key with a set of linear equations. These equations result from the positively answered equality queries that are likely to be issued during decryption, and their linear subspace will be used by our modified decryption algorithm. Let me just note that for simplifying the presentation even further, I will assume in this part of the talk that the public parameters, secret keys, and ciphertexts consist of group elements only. For describing the process in which these equations are formed, let me introduce the following notation. For a generic algorithm A that receives as input group elements G1 to Gk in addition to the group element 1, we denote by EQ of the computation of A on G1 to Gk the random variable corresponding to the set of all k plus 1 dimensional vectors over Zn resulting from the positively answered equality queries in this computation. More formally, for any equality query ij that was positively answered during the computation of A, we can write Vi and Vj, the corresponding elements at the table in positions I and j, as linear combinations of the elements 1 and G1 to Gk by keeping track of A's group operation queries. Therefore, we can express Vi minus Vj as a linear combination of these elements, and then we add the k plus 1 dimensional vector of their coefficients to the set. Given this notation, at a high level, our transformation replaces each secret key SKID with the union LID of several such EQ sets corresponding to invocations of the decryption algorithm with the secret key SKID and an encryption of a randomly chosen message bit B. The modified decryption algorithm will then emulate the scheme's decryption algorithm using symbolic variables instead of the group elements included in SKID, while responding to equality queries using the linear subspace spanned by LID, as I will describe next. Let's look at our modified key generation algorithm a bit more formally. The modified key generation algorithm first generates an identity secret key using the scheme's key generation algorithm. Then the modified algorithm encrypts and decrypts a random bit B for m times while recording the EQ sets of all the linear equations that result from the positively answered equality queries during the computation. Notice that these equations involve the group generator 1, the group elements in the public parameters, and the group elements in the identity secret key. The modified key generation algorithm then outputs the union of these sets, which we denote by LID. Intuitively, when encrypting and decrypting one more time, we do not expect to discover any new equalities that are not already included in LID, and that's the reason that our decryption algorithm introduces only a polynomially small decryption error. Specifically, we prove a simple lemma showing that if x1 to xm plus 1 are independent, identically distributed random variables over subsets of a linear vector space V, then the probability that xm plus 1 is not contained in the subspace spanned by x1 to xm is at most the dimension of V over m plus 1. Now let's look at our modified decryption algorithm. As we mentioned before, it emulates the scheme's decryption algorithm using symbolic variables instead of the group elements included in SKID. Specifically, whenever it encounters an equality query ij, it first expresses the difference between corresponding group elements vi and vj as a linear combination of the symbolic variables and of the actual group elements that are given as input. These are the generator of the group and the group elements included in the public parameters and ciphertext. At this point, we would like to replace the linear combination of the symbolic variables in this difference with a linear combination of the generator and public parameters. If you can do that, then this will enable us to replace this query with an equivalent query which does not include the symbolic variables. That's exactly where the subspace spanned by LID comes into play. If we can find such a replacement, then we query the oracle with the new equivalent query and continue the emulation using its response. If we cannot find such a replacement, then we answer the equality query negatively. Using our lemma from the previous slide, we do not expect to discover any new equalities that are not already included in the space spanned by LID, and therefore the emulation is correct with high probability over the internal randomness of all algorithms. So that concludes step 1. In step 2, as I mentioned earlier, we prove that any generic group IBE scheme whose public parameters consist of NPP group elements and whose secret keys do not contain any group elements may support up to NPP identities. This is proved by presenting a generic group attacker that breaks the security of any such scheme that supports more than NPP identities. Our attacker issues a polynomial number of group operations and equality queries and is otherwise unbounded in terms of additional internal computation. This flavor of efficiency is standard in the generic group model, and it suffices in order to rule out generic group constructions. For describing our attacker A, we assume for simplicity that the integers 1 to npp plus 1 are included in the scheme's identity space, but these can clearly be replaced with any sequence of npp plus 1 distinct identities. Our attacker first samples an identity I uniformly at random from the identities 1 to npp plus 1. The identity I is set as our attacker's challenge identity ID star, and 1 to I minus 1 are the identities for which our attacker requests identity secret keys. At this point, our attacker receives the public parameters, the identity secret keys corresponding to the identities 1 to I minus 1, and a challenge ciphertext, which is an encryption of a random chosen bit B for the challenge identity I. Now comes the interesting part. First, A uses the I minus 1 secret keys in order to learn information about the public parameters. In the next slide, we will see exactly what A needs to figure out and how this is done. Then, using the information learned about the public parameters, A constructs an alternative secret key for the challenge identity I and uses it for decrypting the challenge ciphertext. Let's discuss how A uses the I minus 1 secret keys to learn information about the public parameters, and let me just reiterate the fact that this is a simplified description of the attacker that ignores many technical details. Essentially, A uses SK1 to SKI-1 for learning the EQ sets corresponding to their identities, hoping that this information will contain the EQ set corresponding to the challenge identity. For each j from 1 to I-1, the attacker finds the set EQJ of equations that result from the positively answered equality queries when encrypting a random bit for the identity j and then decrypting it for m times, where m is a certain polynomial. Then the adversary emulates a fresh oracle and searches for alternative public parameters pp star, master secret key msk star, and secret key sk star j that are in the support of the setup and the key generation algorithms, and such that the following two properties hold. First, pp star should satisfy the constraints induced by the previous equations. Second, the probability of finding a new equation that is not in the span of the previous ones is upper bounded by a certain constant. If A finds such pp star, msk star, and sk star j, then A adds new equations to EQJ by decrypting using the real oracle O and the real public parameters pp, but using the alternative secret key sk star j. Now the attacker constructs an alternative secret key sk star I for the challenge identity and uses it for decrypting the challenge ciphertext. The attacker emulates a fresh oracle and searches for alternative public parameters pp star, master secret key msk star, and secret key sk star I that are in the support of the setup and the key generation algorithms, and such that the following two properties hold. First, pp star should satisfy the constraints induced by the equations found in the first part of the algorithm. Second, the probability of finding a new equation that is not in the span of the previous equations is upper bounded by a certain constant. If such alternative pp star, msk star, and sk star I are not found, then the attacker outputs a random bit, and otherwise the attacker decrypts the ciphertext using sk star I and outputs the result. Our analysis shows that with high probability, after using SK1 to SKI-1 for learning information, all equations that result from positively answered queries should be known. This comes from a lemma we prove that is somewhat similar to the lemma that we used for step 1. The lemma states that if xj is the union of set of equations we find during encryption and decryption with the actual oracle, public parameters, and secret key, and of the set of equations we find while encrypting and decrypting with the actual oracle and public parameters but an alternative secret key, then there exists some index j such that xj is contained in the linear subspace spanned by the previous ones. This intuitively follows from the fact that the dimension of the linear subspace that contains all of these sets is at most NPP. The analysis then moves on to show that if the index I chosen by our attacker is an index for which the above occurs, then decryption using the alternative secret key with the actual oracle and public parameters, and decryption using the alternative oracle, public parameters, and secret key have the same output, and our attacker wins. Okay, so that's all for this short presentation. We prove a tight impossibility result for constructing generic group IBE schemes. Our main theorem states that any such scheme whose public parameters consist of NPP group elements may support at most NPP identities, and this matches the naive IBE scheme provided, for example, by NPP-independent instances of ElGamal encryption. Thank you for listening.